Hello and welcome to this presentation of our work titled Buddhas, a universal and dynamic graphical password scheme. My name is Panos and this paper is a joint work with Miles Kirby and Atsuhiro Takahasu from UU Bristol and NII respectively. So from the paper's title, one can assume that this work is about user authentication. We know that user authentication is a necessity nowadays, but it is also an old problem when it comes to proposing a usable and secure scheme. Passwordless is the new trend in user authentication, and numerous entities from industry are trying to propose authentication without relying to passwords. So far, biometrics is seen as a usable solution, but the COVID pandemic era made us realize that availability is not always ensured while wearing masks. Additionally, as a runner, I usually experience problems with fingerprint authentication when my hands are wet. Moreover, some people might not find Face ID as the most suitable method of identification because they might have a twin brother just like me. For these reasons, a passcode is still required, not to mention the need to use a passcode when you restart your device. As I said previously, there is always an issue when we discuss user authentication schemes, the trade-off between security and usability. How can we make a secure authentication system that is usable at the same time? For pins, for example, we can see that we can make the scheme more secure if we request the user to provide a longer passcode. However, we have seen in the literature that this idea does not always serve as a more secure solution. For example, Wang et al. Showed that this extension offers marginally improved security over 4-digit pins. A study by Market et al. Dedicated to smartphone unlock pins showed that 6-digit pins offer little to no advantage and sometimes make matters worse. On the other hand, we have seen in the literature that graphical passwords are generally considered as more usable. One of the oldest graphical passwords for smartphones is the Android pattern unlock. It is very popular because it is easy to create a password on the 9-node grid by swiping your finger to create a shape that serves as your password. However, as we have showed in the past, users tend to prefer specific nodes as starting and ending points. They also tend to form passwords using a top-to-bottom, left-to-right approach, driven probably by the writing style of their native languages. Additionally, a lot of people seem to choose memorable patterns that resemble letters of the Latin alphabet. Therefore, the APU is vulnerable because human factors may dictate biased input. To make things worse, researchers show that the scheme is also vulnerable to smudge attacks and shoulder-serving attacks. To increase security and maintain similar usability standards, researchers proposed various adjustments to the scheme. For example, password meters such as the one that you see here were found to be more effective in improving the security of pattern locks, and also they showed that pattern locks can be more secure than 4-digit pins. In other work, Aviv et al. Evaluated the effect of using a larger grid instead of the traditional 9-node interface, and they found that this extension of the grid size has minimal impact on the security of the scheme. Another idea was to rearrange the nodes on the grid. Although the authors of this paper claim that this rearrangement offers clear security improvements over the 9-node grid, they also question the usability of that scheme. Other proposals like the CISPAL, where the system guides the user to create a pattern using specific policies, are criticized because they are not usable enough. Finally, other adjustments to the APU, such as the dual superimposed input on the same 9-node grid, can increase security, but they have some impact on usability. Now, the basic characteristic of the alternative schemes, as you saw, is the intention to propose mainly minor structural interventions of the original APU scheme that will not drastically harm users' familiarity with the interface. This is because a dramatic alteration might cause frustration and disapproval. Moving from the APU, we have also seen the proposal of alternative grids and methods for user authentication that depend on floating or rotating grids, just like those that you see here, or other gesture-based methodologies. However, these schemes are not usable enough, and sometimes they are not easy to be implemented for small screens. Finally, the literature also features ideas about using shapes and dynamic grids for user authentication. Schemes like those seen in the current slide use symbols such as the circle, the square, and dynamic grids for PIN-based authentication. Given that dynamic grids add robustness against solder surfing, according to previous research, we were motivated to propose a scheme that combines the APU and the use of dynamic grids. So in this paper, we propose a scheme that blends the APU's popularity with the positive effects of using a dynamic grid. We present Buddhas, the first user authentication scheme based on the APU 9-node grid with a little twist. First, inspired by the Morse code, which uses bullet points and data and dashes to create letters and phrases, we are adding simple shapes to enlarge the password space of our scheme. We use the same 9-node familiar APU grid and the same method of creating a passcode by swiping the finger on the screen. However, instead of having a static grid that features bullet points only, we propose the use of a dynamic grid that features nodes that keep changing when the users swipe the fingers on the screen. The most frequent question I get about Buddhas is, why did you choose these symbols? Because these are the least complex according to the literature, and they have been also used previously by other researchers, as you saw in the previous slides. Furthermore, these symbols are everywhere in our daily lives, and we should feel quite familiar with them. So how someone forms a Buddha's passcode? On the top corner, you can see an example of someone forming a passcode, and the rules are as follows. The password is formed as a sequence of symbols from the following set. You can see circle, square, triangle, dash, X. The preferred password must be 4 to 9 symbols long, like APU. The preferred password must contain at least 2 different symbols. The password is formed when users swipe their fingers on a 9-node grid that keeps changing when we visit a new position. Users are allowed to swipe the fingers in the neighborhood nodes only. Therefore, jumps to a distant node are not allowed, unless the user chooses a night move as seen in blue in the figure. Users are allowed to revisit the node on the grid as many times as they need. That's to make the scheme more usable. Now, in order to gather people's feelings about the proposed scheme, we conducted a series of studies. The first accepted study was performed online, like a digital pen and paper study. We requested the respondents to provide a Buddha's passcode that they would use on their devices. And the survey was completed via the web or on the participants' devices, either using Android or iOS. The request was to provide an easy-to-use and secure password. And we call this group of people as the survey group in our paper. The sample was 65 people, and we had to remove some respondents from the pool, either because they did not provide their full consent to participate or they did not answer all requested questions. At the second phase, we wanted to understand how users would interact with the scheme on a device. Therefore, we developed an app which was distributed on Google Play under the education category, and we gathered data derived from users' interactions with the Buddha's scheme. This interaction happened in 2 stages. First, we had 14 users providing Buddha's passcodes using the scheme on the devices. and we named this group as the pilot group. Then we added a memory game to the app and asked a different pool of people to interact with the scheme and also to play a memory game. As you can see, the users first provided demographics, then they saw instructions about how to create a Buddha's passcode, then they created the passcodes and confirmed them similarly to what they are doing when they're forming an APU passcode. And finally, they had the chance to play a memory game that had three different difficulty levels. The users were seeing a Buddha's passcode and they had to recall it. Please note that the shapes in the instructions were randomly fetched here, as we were aiming to reduce any possibility of introducing any biases. Considering the password space of our methodology, we can see that for a 4-node passcode, there exists 620 different alternatives. This is because we have 5 choices for the first node: circle, square, triangle, dash, X. 5 for the next one, 5 for the next one, and 5 for the final one. We should, however, exclude 5 4-node passcodes that consist of the same symbols as the forming instructions dictate. Therefore, we end up with a password space that is 6 times larger than the one that the APU defines. And we can indeed see that the APU schemes seems to provide more alternatives when we're forming short passcodes, but this is not 100% valid because of the bias input that we have already discussed previously. So let's talk about the results. I remind you that we asked 2 questions to the survey group. The first one was to write down the password that you choose, and the second one, the second question is: would you use the Buddha's passcode scheme on your device? Which scheme would you use, the Android pattern lock or the Buddha scheme? And please explain why. Most of the participants were young people identified as males, undergraduate students who were using iOS, but they were familiar with the APU. They were using a passcode on their devices, and most of them were also utilizing biometric authentication. Please notice that the sequence of symbols was not changing in this survey, so all respondents saw the symbols you see with that order, specific order. The first conclusion we can make is that the Buddha scheme is comprehensive, and the provided instructions were enough for people to understand what they need to do in order to form a passcode. We derive this from the fact that although we did not have any input validation in place, we did not get invalid inputs from the respondents. From the frequency analysis of the passwords we collected, we can say the following. Most passcodes started with a circle, and the dash and X were not preferred as starting points in the group. Also, the appearance of symbols is almost uniform in this password set. We could also see that most provided passcodes that have a length of 6 nodes, and mostly 3 to 4 different symbols were used to form these passcodes. So the provided passwords were empirically quite complex. From the participants' responses, we can also see that they were divided in terms of their preference between the APU and Buddhas. However, although most of them were iOS users who were using biometrics in their daily routines, they finally expressed mostly positive adaptation attitudes. Half of those who expressed a negative opinion did not comment on the actual scheme, but they stayed on the convenience of their current user authentication methods and biometrics. For the pilot group consisted mostly of undergraduate students identified as males using biometric authentication, and their main device was running Android. Here we must say that only 2 of the 14 users provided a password that started with the same shape as the one that was first depicted in the instructions. Thus, we can derive that the app does not implicitly create biases. The results we derived from this group of users show that although users envision and formulate on paper long and complex passwords aiming to advance security, they eventually end up with shorter and less complex passwords for the first time that they formulate a Buddha's passcode on their devices. So most collected passcodes start with an X, and we saw that the least preferred, we see that the least preferred symbol was the dash, which also appeared less frequently in the set. Additionally, you can notice that the majority of users provided passcodes with a length of 4 symbols, and most passwords contained only 2 different symbols. In the auxiliary group, most participants identified as males, Android users familiar with the APU, using biometric authentication on the devices, and 56% were undergraduate students. The rest had at least one university degree. Commonly with the previous group, we can see that the most passcodes start with an X, and the dash is the least preferred symbol. Again, the majority of collected passcodes are 4-node passcodes, but in this group we noticed that participants preferred to use mostly 3 different symbols to form their passcodes. So in this group we can say that there existed more entities that tried to provide additional complexity. So the data from participants that interacted with the Buddha's grid show that almost 69% of users that formed a short Buddha's code preferred to include at least 3 shapes in the passcode. Another positive thing is that we did not encounter any particular passcode to be prevalent in the whole password set, which is encouraging compared to the APU, where we always find a preference in using specific passcodes. However, we agree that this might be because the sample in our study was not very big. However, we can derive from this pilot study that the collected passcodes were quite diverse. Finally, from the memory game, we can see that the 4-node password was easy to recall, but that as the passcode becomes more lengthy, the completion or the success rate shrinks. This is expected, and we see the same trend in other graphical password schemes as well. However, a long Buddha's passcode can be easily memorable. For example, a passcode that is formed of 4 squares and 5 dashes can be very, very memorable. Some additional results that are not included in this paper but can be found in the extended version of this work that is currently under review show that usability of the scheme is comparable to LG's NOC codes, and that if we consider the human factors that lead to biased input on the APU, we can see that Buddha's offers a wider password space than the APU. Finally, we can perform n-gram frequency analysis, and we can see we can use these results to create password meters and block lists. These are ideas for further work. To conclude, we presented pilot studies about our proposed graphical password scheme, and we found good acceptance rate within non-Android users. Users that interacted with the scheme preferred shorter passwords, but with an intention to add complexity. No particular biases were identified, except the preference to the X symbol as a starting point. The scheme is robust against smudge attacks, shoulder surfing, and it is usable, especially when the passcode is not long, and it is universal and inclusive because it only uses symbols. Big limitation is that the small scale deployment of our work. Further work, there needs to be some work to validate and extend results with a larger scale study to quantify complexity and propose password meters or the use of block lists. We could see how the use of mnemonic rules can affect the usability, and we can see what is the security and usability impact if we add more symbols in the scheme. Thank you for your attention. I'm happy to answer any questions.